So the second type of bonding that we'll be studying is called covalent or molecular bonding. And covalent or molecular bonding occurs between nonmetals and is the result of the sharing of electrons. So previously we had summarized the octet rule as being that when atoms form chemical compounds, atoms of those elements either transfer or share electrons so as to obtain a noble gas configuration of the atoms involved. So we said that transferring electrons is what happens when we have ionic bonding and form ionic compounds, but sharing electrons is what happens when we form covalent bonds and form molecular compounds. So it's worth contrasting the difference between molecular compounds and ionic compounds. So molecules are discrete little bundles of atoms that are held together by molecular or covalent bonds. And it's important to recognize that the formula of a molecular compound indicates how many atoms are in each type, are in one molecule. So for example, if we have a molecular element like H2, the H2 is indicating that element is composed of molecules containing two hydrogen atoms bonded together. Similarly, if we have Cl2, we understand that a molecule of Cl2 contains two chlorine atoms bound together. If we look at a compound where we have different atom types, something like H2O, this formula is indicating to us that in each molecule of H2O, there are two hydrogen atoms and one oxygen atom. So, yeah, that's an important idea. The formula represents the number of atoms of each type in one molecule, and a molecule is a discrete little bundle of atoms. Now, covalent compounds form as a result of electron sharing between non-metals. So you can see in each case here, we have two or more non-metal atoms bound to one another, and what's holding them together is what we call electron sharing, and we'll see how that works a little later on. Now, if we contrast this with ionic bonding, what we have in ionic bonding is we have a crystal with a repeating pattern of anions and cations that continues approximately infinitely in all directions. And that crystal has an overall neutral charge because we have an equal number of positive and negative charges that kind of cancel one another. And the crystal organizes itself so that those ions with opposite charges are closer to one another than those ions with the same charge, and in that way attractions overpower repulsions and the whole thing holds together. So ionic compounds are formed between non-metals and metals as a result of electron transfer, and ionic bonds are very, very, very strong, and so all ionic compounds are solids at room temperature. Ionic compounds typically have a lot higher melting points than covalent compounds. Covalent compounds can be liquids and gases as well as solids at room temperature, but ionic compounds are always solids at room temperature. For ionic compounds, there are no molecules. They're just this approximately infinite array of anions and cations. So what the formula represents in this case is the smallest, simplest combination of anions and cations that results in no overall electrical charge, what we call charge neutrality. And we know that we can use the crossover method to obtain that ratio of cations and anions. So now we have to look at how this sharing of electrons occurs and how it helps atoms obtain a noble gas configuration. The simplest molecule to consider is that formed by two hydrogen atoms, because a hydrogen atom just has one proton and one electron. So if I have two hydrogen atoms that are separated by a large distance, neither of them will have a noble gas configuration. They will each have one proton and one electron. Now, if those two hydrogen atoms come together and collide, and the region of space that single electron is in, it's a 1s orbital, then they're going to be able to share those electrons. So let's see what happens when they do that. So when these two atoms come together, their electrons, the orbitals that their electrons are in overlap, and what we find happens is that the electrons always end up sitting exactly halfway between the two nuclei in that little bit of space in there. And then the atoms get stuck. And the reason for this is because now each of these positive nuclei feel an inward attraction towards those two shared electrons. So there are some repulsions, of course. There's a repulsion between these two protons, but that's at a bigger distance, and it's just a single plus with a single plus. And there's also a repulsion between these two electrons, but again, it's a fairly large distance, and it's just a -1 with a -1. So the overall effect when these two atoms organize their particles like this is that the nuclei are attracted inwards towards those two shared electrons. And we can also see that each hydrogen atom gets a share of 2 electrons, which is just like helium, which is hydrogen's nearest noble gas. So 2 hydrogen atoms come together, they get stuck to one another and form an H2 molecule, which is consistent with our understanding that hydrogen is one of our diatomic elements. So if we compare ionic compounds and molecular or covalent compounds, what we see is this, is ionic compounds always contain elements that are a long way apart on the periodic table. They always contain metals and non-metals, and they're held together by the attraction between oppositely charged ions. There are no discrete molecules in an ionic compound. They exist as a crystal with an approximately infinite array of cations and anions, and all ionic compounds are solids at room temperature because ionic bonds are very, very strong. Now, molecular compounds are also called covalent compounds. They contain similar elements. In fact, what they contain are similar non-metal elements, and sometimes it's even the same non-metal element. And what's holding the atoms together in a molecular substance is the attraction towards shared electrons by the nuclei. So the building block of molecular compounds is the molecule, which is a fairly small, not infinite, fairly small bundle of atoms, a discrete little bundle of atoms. And the bonding between molecules, well, there are no bonds between molecules. There are sort of some weak attractions sometimes. So as a result, molecular or covalent compounds can be either solid, liquid, or gases at room temperature. So just like we did for ionic compounds, where we use Lewis symbols to show how electrons were transferred, we can use Lewis symbols to show how electrons are shared in covalent compounds. So here's a hydrogen atom. It's in group 1A, so it has one dot in its Lewis symbol. And here's a fluorine atom. It's in group 7A, so it has 7 dots in its Lewis symbol. And if these two atoms come together, what do we see? If they share these guys here, think of those unpaired dots as being like a hand looking to reach out and grab a partner. If they share those 2 electrons, then we find that every atom now has a noble gas-like configuration. Hydrogen loves to get 2 electrons, so it can be like helium, and then fluorine likes to get 8 electrons, and that gives it an electron configuration like any of the other noble gases. So it has a stable octet. So these 2 electrons that are in between the atoms, they are shared. And what we will often do is a shared pair of electrons will replace it with a line. The line indicates what we call a bond. So that line represents 2 electrons being shared. Notice there are also these other electrons out here. We call these guys lone pairs because they belong to a lone atom. They're not being shared and they don't help the molecule stay together. So fluorine we know is a diatomic element. Why is it that when 2 fluorine atoms come together, they get stuck? Well, what happens is when they come together, they pair up these unpaired dots here. Again, these guys are in group 7A, so we've got 7 dots around each fluorine. They come together and then they share those electrons, and that gives us a single bond in there. So we call that just one line, we call that a single bond because it's a single pair of shared electrons. And then each fluorine has 1, 2, 3 lone pairs on it that are not helping hold the molecule together, but they are completing the octet of the fluorine atom. Here's bromine, it's also in 7A, coming together with a fluorine, which is in 7A, and what's going to happen, these guys are going to pair up and they're going to become shared between the two atoms. So there's our bond in there. So a covalent bond is simply a shared pair of electrons, and then we're replacing that shared pair of electrons, the two dots there, with a single line. And again, each element here has 3 lone pairs. And if I look at any one of the atoms in this molecule here and count up the electrons, we see that they both have a stable octet. So 2, 4, 6, 8. It's got 8 electrons. 2, 4, 6, 8. We've got 8 electrons. So that's the general concept. So we see in a molecule there are 2 types of electrons. There are those electrons that are shared, we call those bonding electrons, and one pair of a pair of electrons forms a single bond. So this is one bonding pair, one bonding pair, one bonding pair, one bonding pair, or alternatively we say a single bond, a single bond, a single bond, a single bond. Now there are these other types of electrons that are not being shared, they just belong to a single atom, and we call those non-bonding electrons. Non-bonding electrons. And non-bonding electrons are often described as coming in lone pairs. So 2 non-bonding electrons is referred to as a lone pair. So if I look at this fluorine atom over here, it has 2 bonding electrons and it has 6 non-bonding electrons. Another way of saying 1, 2, 3, 4, 5, 6, right? 1, 2. Another way of saying this here is that this fluorine has a single bond and it has 3 lone pairs. So you do have to be a little bit careful about whether questions are asking you for the number of pairs of electrons or the total number of electrons. You've got to be a little bit careful there when you read questions. Lewis structures can be used to depict bonding in molecules that are bigger than 2 atoms. So here we are showing how a water molecule forms. Hydrogen's in 1A, it's got 1 dot. Oxygen's in group 6A, it's got 6 dots around it, and you can see these unpaired dots come together to form bonds, and that's how we form an H2O water molecule. So in a water molecule we see that there are single bonds from the oxygens to the hydrogens, and the oxygen has 2 lone pairs on it. Here we are. Now interestingly, when we look at the Lewis symbol for oxygen, you see that it's got 2 unpaired dots there, so that's an indication that it loves to form 2 bonds. Okay, here we go to nitrogen here, combining with hydrogen. Nitrogen's in group 5A, so it's got 3 unpaired dots in its Lewis diagram, or its Lewis symbol. And then here is the hydrogen atoms that are in group 1A, and you can see these guys are going to pair up and form bonds, right? So there they are, forming bonds. And by doing this, every atom ends up with an octet, except for hydrogen is happy with what we call a duet, and just 2 electrons. So 2 electrons for this hydrogen, 2 electrons for that hydrogen, 2 electrons for that hydrogen, and then the nitrogen in the middle, 2, 4, 6, 8. So the nitrogen forming 3 bonds and 1 lone pair. Okay, here's carbon. Carbon's in group 4A. It's got 1, 2, 3, 4 dots in its Lewis symbol. The hydrogen's still got 1 dot. They're in group 1A, and you can see how these guys are going to share electrons so that the carbon ends up with a stable octet and the hydrogen ends up with a duet like helium. So every hydrogen here has a share of 2 electrons, and then the carbon in the middle, 1, 2, 3, 4, 5, 6, 7, 8. Now, we're going to replace the shared pair of electrons in each case with a line, just to make it simpler to see what's going on. And there we have what we call a methane molecule, CH4, carbon bonded to 4 hydrogen via single bonds with no lone pairs on the carbon. Okay, so mentioning in this for, I guess it's the third time now, the number of unpaired dots in a non-metal atom's Lewis symbol indicates the number of octet vacancies and the number of bonds it tends to form. Now I should point out that there are exceptions. Later on we will see carbon forming 3 bonds to oxygen, and you can see that neither carbon or oxygen would like to form 3 bonds. So there will be exceptions, but most of the time it follows these rules. This rule of octet vacancies equals the number of bonds that the atom likes to make. Now, we've already talked about single bonds. They are 2 shared electrons. You guessed it, if we share 4 electrons, we get what we call a double bond, and if we share 6 electrons, we get what we call a triple bond. So in water, we see 2 electrons being shared between the hydrogen and oxygen atoms, and they are single bonds. But if we go to something like dinitrogen, so 2 nitrogen atoms come together, and they're going to share a total of 6 electrons, that is 3 pairs of electrons, so that's going to give me what we call a triple bond. And if we go to oxygen, 2 oxygen atoms collide with one another, what are they going to do? They're going to pair up all of their unpaired electrons. That gives us 4 electrons being shared, or 2 pairs of electrons, and so that gives us what we call a double bond. So bonds can be either single, double, or triple. We've never observed a quadruple bond or higher. Okay, now you probably can recognize fairly quickly that if an atom wants to form a multiple bond, that is, it wants to share 4 electrons or more, then it has to have 2 or more octet vacancies. So that rules out hydrogen from forming double bonds, and it also, or triple bonds, and it also rules out any of your elements from group 7A. They simply don't have enough octet vacancies. So elements that are in group 6A, they have 1, 2 octet vacancies. So there's a couple of options for those guys. They can form 2 single bonds with 2 lone pairs, or they can form 1 double bond with 2 lone pairs. The group 5A elements, that's the nitrogen group, they have 3 octet vacancies, so they can do a little more. They can form 3 single bonds with 1 lone pair. They can form a double and a single with 1 lone pair, or they can form a triple bond with 1 lone pair. But you'll see in all 3 cases, the total number of bonds adds up to 3 bonds. So when we go to group 4A, the non-metal in there is carbon, and it has 4 octet vacancies. And so that means that it can be really versatile in its bonding. It can form 4 single bonds, it can form a double bond and 2 single bonds, it can form a triple bond and 3 single bonds, or it can form 2 double bonds. And so this is why carbon is so prevalent in biochemistry, because it's the most versatile non-metal. It can do all of these different bonding patterns. So we see carbon in our DNA, we see carbon in our proteins, we see carbon everywhere in living systems, and the entirety of organic chemistry and biochemistry is mostly concerned with the chemistry of carbon and its compounds, because carbon is just so versatile in its bonding. Okay, so let's have a look at some of the ALEX type problems. So the first one here is concerned with counting bonding and non-bonding electrons in a Lewis structure. And the Lewis structure they give you is that of the hydrogen fluoride molecule. So we've got hydrogen, and there are 2 electrons that are being shared, and then the fluorine has got 3 lone pairs on it. You have to read these questions carefully. It says count the number of bonding, and there it is, pairs, and the number of lone pairs around the hydrogen atom. So there's the hydrogen atom there. And so what does it have? It has 0 lone pairs, and it has 1 bonding pair. And you'll see what I'm meant by you've got to be careful about whether they're asking for the number of bonding electrons or the number of bonding pairs. Okay, here's another one, a little more complicated molecule here. So it says below is the Lewis structure of the hydrazine molecule. Hydrazine is often used as a fuel in rockets. And then it says count the number of bonding pairs and the number of lone pairs around the right nitrogen atom. The right nitrogen atom. So there's the left one, there's the right one. So we're talking about that guy. So what does it look like? Nitrogen, it's got 1 lone pair, then it's got 1 bonding pair to its right to the hydrogen, and then it's got 2 bonding pairs to the other nitrogen. So 1, 2, 3 bonding pairs, and then 1 lone pair. So you have to read the question carefully, and you have to kind of count carefully, make sure you get the correct nitrogen atom, make sure that you're counting pairs and not individual electrons. So you just got to read carefully and be kind of calm with it. Okay, so that concludes this section on the formation of covalent bonds. Hope you found the video helpful. Good luck with everything.